Greetings, we are Team Ares Robotics from Netaji Subhas University of Technology, India. Since the past 4 years, our team has been able to successfully improvise and upgrade our rovers. With over 100 student members from various disciplines working diligently day and night, we present you our rover Pegasus.
I am from electronics department. We have designed the nervous systems, PCBs and motor drivers. We also conducted the field test and debugged the rover circuitry. Professional softwares like EasyEDA and LTSpice have been employed to ensure proper working under specified conditions.
The mechanical team designs, manufacture, and assemble the framework, robotic arm, and the hardware for the live detection subsystem. This year, we aim to develop a modular, lightweight rover with increased robustness and strength.
The Ares science team is responsible for analyzing the different parameters useful for detecting microbial life on the surface of Mars. The rover is designed to conduct various onboard tests which will give us the data related to extinct, extent, and no life.
This time our team has made an entirely new approach where we divided our system into further subsystems to reduce the interdependency.
The software team is responsible for designing and implementing algorithms which aid the rover in autonomous traversal. We incorporate technologies like computer vision and ROS to complete a navigation task and to perform AR tag detection. We operate on the interface level to utilize the intercomponent interaction to achieve complete, independent, autonomous traversal.
The business department has played a vital role in the efficient functioning of the team. We were able to raise significant amount of funds from various corporate collaborators, crowdfunding, and also received our university support for the development of our rover.
For the autonomous navigation task, team uses a stereo IR-based depth module. We implemented visual inertial audiometry using continuous slam with depth cameras. Taking the starting point of the rover as origin, an extended Kalman filter framework is used to fuse the continuous data consisting of the encoder feedback as audiometry and the data coming from the IMU to get the local state of the rover. In addition to this, whenever the GPS coordinates are available, they are also fused to get the global state of the rover, which includes the velocity, orientation, and heading direction.
In architecture, Jetson Xavier is employed to perform all the autonomous tasks. Here we have used master-slave configuration where Jetson is used as master and other microcontrollers as slaves. Two separate communication channels are used to do data transfer and for video streaming. Blinking of blue color LED will ensure the proper working of entire system. To ensure the safety, we have used a kill switch to immobilize the rover in case of catastrophic failure.
The autonomous framework runs on Jetson Xavier, which has 6-core NVIDIA Calm Alarm. The entire pipeline is implemented using robot operating system. ROS nodes are used to carry out the individual tasks as well as to generate commands to control each motor independently. As field testing was limited, gazebo-based simulations were extensively used to test out the robustness of the system in a variety of terrains due to the lack of time for field testing due to COVID-19. Using weight disparity map-based approach, a point cloud is generated and then using the PCL library, the surface, normal and ground plane is estimated, after which we get the obstacles by subtracting the ground plane from the original disparity map, which are triangulated in a 3D point cloud and are then visualized using OpenGL. We use a motion planning framework based on modified A-style algorithm implemented in C++, which takes into account the rover state and dynamic constraints. For post and gate detection, we use the augmented reality library RUCO, which gives us the ability to detect as well as localize the markers when detected, thus in turn helping us with AR tag detection. These markers are then localized in the global map so that the path planning algorithm can generate commands accordingly. We have implemented the graphical user interface for smoother rover control. The interface was made using Electron.js and is being rendered as a local software application required for communication with the rover. It displays important information like motor speeds, direction, distance traveled, camera feeds, and forward-backward speeds. In addition to this, the interface also provides the option to toggle the autopilot in our rover in case manual control is required.
The mechanical team this year aimed to develop a modular lightweight rover with increased robustness and strength. This year we have implemented a 4-wheel trailing arm suspension system with dampers that provide extreme traversal capabilities and impact endurance. Suspension and traversal system rigidness has been tested on rocky, sandy and grainy terrains including multiple craters and falls. The rover can climb obstacles up to 0.5 meter and can descend a drop of 1 meter with great ease. To provide surface traction and high stability with uniform load distribution, balloon wheels with custom threads are introduced, with customized aluminum wheel hub that mitigates motor from damage through uneven terrain. A tubular space frame box chassis comprised of aluminum 6061T6 square channel joined using TIG welding makes the rover more tough, rigid and robust by providing high strength to weight ratio and also serves a mount for auxiliary modules. This year we completely redesigned the robotic arm with the implementation of inverse kinematics to achieve great accuracy and precision. Our 5 degree of freedom articulated robotic manipulator is fabricated using laser cut aluminum linkages featuring 2 linear actuator and brush DC motors with encoder which can lift a payload up to 6 kg. The end effector comprises of a spur gear mechanism and a lead screw based gripper for pitch, roll and gripping action that provide precision and versatility to grab any shape and size. A worm gear mechanism is used to provide 360-degree rotation to the manipulator. Structural interface components have been analyzed and optimized using finite element method which confirms the lightweight and high strength attributes of the subsystem.
For performing the science task, we have used an auger-based drill mechanism with the help of a linear actuator. A helical shaft is attached with the drill to scrape out the soil sample on site. The soil collected is stored and used for different science tasks like lysis to study the microbial life. For filtration and lysis, we have designed a blender for mechanical agitation and chemical lysis. Our filtration assembly consists of a sieve and a membrane filter. After performing lysis and filtration, our rover is designed to perform the following reactions: Sakaguchi test, Sudan 4 test, strip test, and shift test. The science system comprises of pH, atmospheric pressure, moisture, relative humidity, luminosity, temperature, methane for the chemotaxis part, and ammonia sensors. For basic preliminary analysis of soil, we have implemented chemotaxis that takes into consideration the movement of our rover towards increasing gradients of biosignatures. In the science department, we are using a microscope to detect texture and to extract data about soil morphology with the help of OpenCV. This microscope takes picture of the site with high resolution and focus which can be analyzed with AI. For observing the colorimetric changes, we have designed a visible spectrophotometer which uses a PET transmission grating.